self-dual and anti-self-dual. So correspondingly, the curvature of connection will split in this case, the self-dual anti-self-dual part. So so we've got the first variation calculation of the Yang-Mills function, the Yang-Mills equation here. It turns out that if one of these pieces vanishes, that automatically satisfies the Yang-Mills equation. So the basic idea is that, well, let me report this now. So just using Hodge theory, you can, so the adjoint operator shows up in the first variation. All right, and then depending upon your conventions, your sign conventions and everything, there might be a plus or minus here, but anyway, you can rewrite this, the adjoint in terms of the actual exterior derivative, and then conjugate by the star operator. This leads to the following definition. So a connection is self-dual or anti-self-dual if the curvature is self-dual or anti-self-dual. So i.e., if, let's see if I get this right, so self-dual if the minus part vanishes, and anti-self-dual means the plus part vanishes. And then you can check using this formula that if, so maybe put it over here, because we're getting a little small already. So if nabla is self-dual or anti-self-dual, then nabla is the Yang-Mills connection, satisfies the Yang-Mills equation. All right, so you just check this by using the second Bianchi plus this expression for the adjoint. All right, so it's a critical point, but actually you can say, well, to do that, you need to consider topological variance, so namely, choose the Chern classes. So the second Chern class model is given by, and again, it depends upon your conventions, but for me, I guess it's going to be minus 1 over 8 pi squared. And the form you integrate after you simplify turns out to be the difference squared of the self-dual and anti-self-dual part of the curvature. So this tells us very quickly that, in fact, not only are self-dual and anti-self-dual connections critical points, but actually they have to be global minimizers. So you can rewrite the Yang-Mills energy in terms of the second Chern class the following way. So the Yang-Mills connection is plus or minus 8 pi squared second Chern class, and then plus 2 in the self-dual or anti-self-dual part of the curvature, just by splitting the curvature and then using the formula for C2. Well, if you want to think about this as U2 bundle, that's fine. I don't care. So the point is we get a lower bound of this form. And I want to highlight this and hopefully not erase it because I'm going to come back to this later on. So the corollary is that, so nabla is self-dual. So if nabla is self-dual and anti-self-dual, then nabla is a global minimizer of Yang-Mills function. Oh, yeah, so I should say, whether it's self-dual or anti-self-dual, in either case, the term used collectively is instantons. So instanton solutions are of fundamental importance in the applications of gauge theory to fundamental topology. But that's a very different story from what I want to talk about today. So let me begin to explain what I have in mind. So as I mentioned at the beginning, this is really a talk about some variational properties of the Yang-Mills function. So the first kind of results I want to talk about are so-called gap results. So let me phrase it this way. So same setup, a vector bundle over a 4-manifold. And now let's suppose I have a Yang-Mills connection. So here's the kind of question I want to ask. All right, so one kind of, if it's a Yang-Mills connection, it could be an instanton. So maybe it's, let's say self-dual. Well, actually, the way I'm going to write it is anti-self-dual. So it could be anti-self-dual, so the plus part of the curvature vanishes. So that's one possibility, but suppose that's not the case, so this is not infinitely zero. Then is there necessarily some discrete gap in the Yang-Mills energy? So a little more precisely, does there exist a number delta, which is certainly going to depend on the bundle, such that one solution, actually, we have that instanton, so that's self-dual. So either this, for a Yang-Mills connection, either it's self-dual, which is anti-self-dual right here, or it has to be above this energy level. Okay, so there's a number of results along this line in the literature. We hit on a few here. Actually, the first one I want to hit on is not exactly in this kind of vein, but it's nevertheless important. So let's do the Bourguignon and Watson back in 81. Okay. And so this is, I guess, this is a sphere. So the result is following. So here I'm doing things in terms of the L2 size of the self-dual part, but they did it in terms of the L infinity size. Anyway, it's the same kind of spirit. So it turns out they have a number, which is 3, and they say if the L infinity norm is less than 3, again, for a Yang-Mills connection, right? Then you have the ASP. 3. So it's later on I'll write down a Bachner formula, and when I write that Bachner formula down, and you specialize in the case of the sphere, it's a competition of 2 terms, and you just realize if this hypothesis holds, the positive term beats the negative term, so it boils down to. Okay, but in the direction of L2 results. No, I guess it's sort of, I have to think about what you mean by sharp. Because in a small set, you're letting it be a little bigger than 3 here. I know where the 3 comes from, and there are examples where, okay, so the standard solution on the force sphere, the BPST is fine, where you will have identically equal to 3. All right, so in that sense, I guess you say it's distributed sharps. But anyway, I'm going to concentrate on the L2 statement. Yeah. Yeah, well, yeah, I think because the algebra doesn't matter for this one, yeah. Because it's from a Bachner formula. So.
Which exists.
Right, so this is S4, and that's what's feeding into the 3.
Right, but there may be a curvature term from the bundle, which
that's what this is.
Oh, that's where it only shows up there.
Yeah, yeah, exactly. Okay, so, but in the L2 direction, there's 2 results about the same time. So now, I guess it's 82 and Parker. I'm going to group these together, different papers, but I'll group them together because they're very similar in spirit. So the answer is yes, there is such a delta. And, okay, what is the delta depend? It's not explicit. And what does it depend on? So I'm going to be a little bit vague here because eventually I'm going to write down the Bachner formula anyway, and it'll be easier to be more precise about what everything depends on. But so the volume of the manifold, and then there's some condition on the curvature of the metric of the manifold, which it's a kind of positivity condition. I'll come back to this later. And then some kind of dependence upon the Sobolev constant. And then, of course, the vector bundle. And the basic idea here is, so for this result, as I said, it's a pointwise Bachner argument. For this result, you use the Bachner argument, and basically you want to do kind of an epsilon regularity, and that's why there's a Sobolev constant dependence here. So it's really epsilon regularity in disguise. So it just says if you have L2 smallness and you beat the Sobolev constant, the only solution is 0. That's what it boils down to. And then more recently is the Phen. So this will be 2016. So here, so again, the dependence is kind of complicated. But so Phen, he drops this positivity condition, and he replaces it with a kind of genericity condition of the metric. So he defines what he means by a good metric, and he shows this as a generic property. And then, so there is such a constant, but it depends upon the metric sort of in a non-obvious way, and then the bundle. But nevertheless, dropping this positivity condition that I'll eventually talk about is actually kind of crucial because this actually has topological implications. So this is a more general result. But in both these cases, I guess you don't really, you can probably estimate delta, but you don't really have a concrete number. Okay, so let me state the first result. I want to discuss our here A, and this is so it basically says that yes, there's a delta, and we can quantify it, and it's more or less sharp, or at least sharp in certain cases. So same setup. But we also make a curvature assumption that I'll get to in a second. So close, oriented. So Nabla is the Yang-Mills connection. Okay, so then the result is the following. I'll stay and I'll explain the notation. So then Nabla is an instanton. Well, let me put this on and do the self-dual part. So then the connection is anti-self-dual, or you get the following inequality. So it says the following. Our result only holds if the scalar curvature of the basis manifold is positive. And we measure that in a conformally invariant way by looking at the Amavi invariant. So this is the Amavi invariant. And this is less than or equal to, so I got to get the constant correct here. So 3 gamma 1 of E, I'll explain in a second. The L2 norm of the self-dual part of the curvature, plus 2 root 6, the L2 norm of the self-dual part of the Weyl tensor. Now, what is this gamma 1? So it's a constant that you can compute, and it depends upon the bundle. But there is a universal upper bound. So depends upon the bundle, but the universal upper bound is always less than or equal to 4 root 3 over 3, depending on your conventions. So in particular, for example, if you're on the sphere, all right, then this is an explicit number. All right, this is just the volume of the sphere. Well, what is the volume? The square root of the volume of the sphere times the scalar curvature of the sphere. So anyway, this is explicit in the force sphere. You can get an upper bound on this constant, and then of course the sphere is conformally flat, so the Weyl tensor vanishes. This term's not there, and so you get a lower bound. So generally you get a lower bound whenever this term is bigger than this term. But if you apply this sphere, let me just mention that, and I bet I erased it. I didn't. Hooray. So the corollary is that if you're looking at a bundle over the force sphere, and then let me, so that we can pin down a value of gamma 1, let's say an SU2 bundle. Just because we know the explicit constant here. And again, Nabla is the Yang-Mills connection. Then either it's anti-self-dual, or this estimate written out tells you that the Yang-Mills energy is greater than or equal to 8 pi squared times the absolute value of the second term class plus 16 pi squared. So compare that with this general inequality here. So this is the same as this, right? So it says that, all right, if you're not an instanton, if you're not anti-self-dual, then the gap here is 16 pi squared. And that 16 pi squared is there are examples where you hit that value. This is full. This is full, yeah. That's why you bring in the second term class, yeah, it's full. All right. So there's two, this is a, wow. So there's 2 ingredients in the proof, and I'll postpone both of them to the second hour. Well, the second part of the talk, I promise they won't both be 1 hour. So the key ingredients. So the first one is, I guess I should have said this when I first wrote down the formula. So one a little bit unsatisfying thing about previous results, just in addition to the fact that you could really quantify these constants, is that it doesn't really reflect the conformal variance of the Young-Mills energy. So all these things, all the data here is kind of sensitive to conformally change in the metric, but the Young-Mills energy is insensitive to conformal change in the metric. So where this estimate here is conformally invariant, every term is. Okay. So and that's crucial for us, and we exploit that in the proof in a key way. So what we want to do is not, if you give us a base metric, we don't want to necessarily use that to do our estimates. And in particular, when we write down the Bachner formula, we do not want to write down the Bachner formula with respect to the given metric. We want to first conformally change it to a more optimal metric. So it's a choice of conformal representative. That's really the only new idea. And then the second key thing is this Bachner formula that I keep referring to, which is well known. So it's just applying this idea to the Bachner formula. And I'll write down the Bachner formula in the second part. Okay, so that's the first thing I want to talk about. All right. And then the second thing I want to talk about are index estimates. Okay, so this first result says you're either at the minimum energy or you have some fixed gap above that. So if I have a non-minimizing solution, so I'm above that energy cutoff, then the next one is minimizers. So you want to look at the second variation and look at the index. You could have directions where the Young-Mills direction, the second where the Young-Mills energy could decrease and increase. So that's the theme of the second. Okay, so the setup now is we always have a export Young-Mills connection. And now we want to do a variation in the second order. So take the same kind of variation we talked about before, but take the second one. Oops. Okay, what do you get? Well, I guess the way I'm going to normalize this with a factor of 2 here, you get an index form. So what happens is some operator, I'll call J for Jacobi, that acts upon B, and you take the inner product of B. All right, so what is this operator? So this operator is the following. It's in terms of the rough Laplacian. I should say, by the way, my Laplacian on Euclidean space is this, okay, just to make it clear on the signs right here. So it's minus the rough Laplacian, and then there's another second order term. So basically what's going on here, this is just going to be the Hodge Laplacian. So it's another second order term. And then a term involving the curvature of the bundle. So I'll write it this way, and I'll say something just a minute about this. And then a term involving the curvature of the base. Okay, so I'm using a lot of abbreviations here. So the bracket operation can be extended to a bracket operation on bundle value 1 forms, and then 2 forms. It can be extended to a bracket operation on 2 forms with the 1 form. So this bracket here will map 2 forms across 1 form to 1 form. Well, let me not write it out because there'll be a boatload of indices and it won't tell you anything that you need to know for this proof anyway. And then the Ricci is a symmetric 2 tensor, and then there's an obvious way in which any symmetric 2 tensor acting on the tangent bundle of the base can be extended to an action on 1 forms, bundle value 1 forms. So we can just view this Ricci as an endomorphism. This. Okay, so due to gauge invariance, we can actually assume that the second term vanishes. So this is a choice of gauge that's always possible. Yeah, exactly. Yeah, exactly. So I'll put. Okay, so without lots of generality, we can assume that that the divergence of B is 0, so that term's gone. So then we can just look at the Jacobi operator. I flipped my bars here. Sorry. Oops. That's it here. Okay. So now we're just going to look at the operator without the second term. And we have so the bracket, write it this way, and then plus Ricci. So there's our operator. Okay, so now with this gauge fixing, we can now view this as an operator. So it's a differential operator on 1 forms. It turns out so the leading term is the rough Laplacian if we've done the gauge choice. So it's elliptic and it's self-adjoint. So let's label the eigenvalues. And because the leading term is minus Laplacian, minus sign conventions, the eigenvalues march off to infinity. So let me label them without multiplicity. Okay. So I can label the eigenspaces. So E lambda 1, E lambda 2, etc., etc. Okay, so the index is just going to be the number of negative eigenvalues, the dimension of the sum of the dimensions of all the eigenspaces associated to negative eigenvalues. So we have the index. So that's denoted I of nabla. So that is going to be the dimension. So I'm going to take the union of all the eigenspaces associated with negative eigenvalues, and then the nullity. So that'll be denoted by nu. So that's just the dimension of E0. So we have a kernel. So what do we want to do now? So for arbitrary, okay, so actually when I state the inventor result, we're going to, as part of the assumption, we're going to assume we're not an instanton, so we're not a minimizer. So we're looking at higher energy solutions. And what we'd like to do is get an index bound. So the rough idea is that if the index is large, right, then the energy should be large. Or, same result just stated the way that you have a bound energy, then the index cannot be too large. Okay, so if you have, if the index is 0, then we say that the connection is stable. That means all the second variation is not negative. Okay, so let me give a little overview of what's known in this case. So again, let me begin with the result of Bourgain and Lawson. That really isn't quite in the spirit of what I'm after, but nevertheless it's an important result. That paper was filled with really fundamental results, in fact. So again, oops. The same paper. Okay, so this is again for bundles over S4, and here the Lie groups are fixed. So this applies to SU2, SU3, and U2 bundle. And it says that stability applies instanton. So this would be an extremely strong kind of statement where, okay, if I know something about the index, then I know something about the variation property of the solution. I mean, it's much stronger than this. Okay, but much more in the spirit of what I want to talk about, where you estimate the index, is a result of Urakawa. And this is in 86. So there's a number of assumptions here in the base manifold. So first, the assumption is that the Ricci tensor is bigger than k times the metric, where k is positive, so you have to positive Ricci curvature for the base. So it's an estimate for the index plus the nullity. So they're bounded by a constant, and the constant depends upon the lower bound on the Ricci curvature, a pointwise norm on the curvature of your Yang-Mills connection, the dimension of the manifold, and the bundle. Okay, so this is in the spirit of what I want to do, but once again, I guess I should say, it's not obvious at all. Well, I guess it falls from the invariance of the functional, but it takes a little more work. But in any case, note that the index plus nullity is a conformal invariant. So once again, the estimate you have here doesn't capture that conformal invariance. You also have the strong assumption on the base manifold, right? And we want to get rid of that. Well, as much as we can. So in the first result, we're going to have to assume positive scalar curvature again. Okay, so let me state what we were able to do in this case. So I'll call this theorem B. Same paper, but all three of us. Okay, so again, a vector bundle over 4 manifold, and now actually the structure group comes into play. So in a sort of mild way, but it does come into play. Okay, so the statement is that, and so Nabla is a Yang-Mills connection. Okay, so then Nabla is an instanton. So this is let me write this little thing a little more carefully here. So it's an alternative. Okay, so either Nabla is an instanton, or you get an index plus nullity estimate. And so the estimate is a bit strange looking, but I'll explain why it's strange looking. It's not our fault, just the technique, so I guess it is our fault. But so you get a strange constant 144 e squared times the dimension of the group, divided by, okay, once again, so Urakawa's result assumes positive Ricci. We're able to soften that to positive scalar. And then again, the Yamavian variant appears. So times the square of the Yamavian variant times, okay, I should have shifted this over here because it's a big, kind of strange expression. So we want the energy to appear. It does. So it's 12 times the Yang-Mills energy. And there's other terms that are conformal invariants. And so once again, the Weyl curvature comes in, just like it did in the first result. So we get 3 times the norm squared of the Weyl tensor. And then there's a strange cross term that comes in that looks like the following. So it's 3 root 2, the norm of the Weyl tensor times the norm of the curvature. When I explain the technique, you'll understand why you get kind of strange constants in this cross term here. And then a topological term, so minus 12 pi squared times the Euler characteristic of the manifold X, the base manifold. So again, everything in sight is conformally invariant, and this tells you that if you have large index plus nullity, then you must have large energy. At 2.718, I can't. Yeah. No, so I will tell you. In fact, let me write down a corollary. Let me make a couple remarks about where this result comes from, and of course also. Well, okay, so you make that assumption when you write down the operator, right? So this is estimated enough. Here you're estimating the number of eigenvalues of this operator, and that operator is elliptic because you made a Coulomb gauge choice. sphere, many of the constants are more explicit and certain terms drop, and it's a cleaner statement. So now if you're S4, so if nuplet is not an instanton,